Hi, everyone. I wanted to go over the module 12 from this week. Let's start backwards and talk about what we covered last week. So last week, we looked at one sample and two sample hypothesis testing. And basically what we did there is an example from the textbook. If we're concerned about a 16-ounce can of sliced pineapples being overfilled, we could have our quality control department take a random number of cans and measure them. Then at that point, what we could do is run the t-test that we ran last week, and that will help us determine whether we are overfilling these cans or are we underfilling these cans. So we can test that. Then we did a two sample, and then the two sample itself, that's using, for example, multiple different types of variables. And in this case, we're looking at two. So an example from the textbook again, a sample of 40 babies using Gibbs products revealed the mean weight gain of 7.6 pounds in the first 3 months after birth. For the Gibbs brand, the population standard deviation of 2.3 pounds. A sample of 55 babies using the competitor's brand revealed a mean increase of 8.1 pounds. The population standard deviation for that brand is 2.9. What we could determine is which one of the brands had the better impact. Okay, so we can test that. We can test that hypothesis. If we believe that ours is better than our competitors, and we can test that. So this week, we're jumping into what is called an analysis of variance. And for short, it's known as ANOVA. So for example, ANOVA helps us to further our hypothesis testing because we can run multiple t-tests, which would then inflate our chances of making an error. Instead, we use analysis of variance, ANOVA, to test them all simultaneously. So for example, if we have multiple variables, we could test them all at once instead of running a t-test each individually. So the variation between groups we can look at. So is there an effect, for example, of a training program between multiple groups? Which group had more of an impact because of the training? We can test that all at once. And for ANOVA, the p-value, if it's less than our alpha, we reject the null hypothesis. So it's similar. So we're going to take a couple of example problems here, and we'll look at those here in just a second. But a couple of more things to make sure we understand. So there are three different ANOVA. So there is a traditional ANOVA that we'll look at. There is a two-way ANOVA where it has a blocking variable, which we'll talk about. And then there is a two-way ANOVA interaction without a blocking variable. So when would you use each? So for example, the two-way ANOVA using a blocking variable, if we want to test three different marketing displays for selling sports trading cards, okay, we use 4 different retail stores locations as our blocks. By blocking the data by location, we strip out the variations caused by the neighborhood foot traffic so we can clearly see the true effect of the marketing displays. Again, we'll look at a real life example of this here and we'll test the values. It'll make more sense here in just a second. And then we have a two-way ANOVA that we look at to see if there's interaction. So we use it when we want to test two main factors at the exact same time. And we want to see if those factors interact with each other to influence the outcome. So for example, if In-N-Out Burger wanted to test whether ordering method matters, for example, is drive-through versus inside register, and the time of the day, lunch versus late night. ANOVA will give us a p-value for the ordering method a p-value for the time of the day and a p-value for the interaction to see if the effect on time of the time of day changes depending on whether the customer uses a drive-through or walks inside. So again, these are just the lecture notes, just highlighting a few things that I think are important. But we'll go back over right now and take a look at our examples in Excel so we can actually go ahead and compute these. So the first problem that we have, we're going to compare the average daily sales across 3 different farm stands, and those are in Oakdale, Ceres, and Salida. So we're going to use our hypothesis testing process that we've been working on from the last week. So for example, we're going to have to first state the null hypothesis and the alternative hypothesis. So our null hypothesis, what we're going to say in this case is that the Oakdale farm stand, the Ceres farm stand, and the Salida farm stand are all equal. There is no difference based on location. Alternatively, we're going to say that at least one location average sales is different. So we can test that using a one-way ANOVA. The alpha we're going to go ahead and choose is 0.05. And the test type, which we already mentioned, it's going to be a one-way ANOVA. And then we are going to state that reject the null hypothesis if the p-value is less than 0.05, which was our alpha. Move that over so it could show up here. And then the decision is going to come into play after we run our one-way ANOVA analysis. So let's go ahead and do that. I'm going to go ahead and go to data. So move up here a little bit. We'll go to data. I've already done it here, but I'm going to replicate it. Data analysis, and then I'm going to use a ANOVA single factor. Press OK, and I'm going to highlight all the values here, the Oakdale, Ceres, and Salida data. Okay, and I'm going to put that in here, and I'm using columns. The data is in columns. And I use the labels, so I mark the labels, and my alpha is 0.05. And I want my output range to just start here, and that doesn't matter where you choose, but I started mine here, 829. And once I do that, press OK. Then I get these values here. So what does this basically say? What does this say to us? So at this point, one second here. At this point, what this tells us is the summary of the data. So we get a summary data, and it does some things like it sums them all up. It gives us an average, and it gives us a variance. Okay, but the one that we want to that we care about the most is the between the groups and our p-value. Okay, here's our p-value in between the groups. So let me actually run this again. So when you rerun this, and I just did it right now, you'll see that at the p-value, you'll get an error. And it's really important to change this error to a number. It's set up as a general value, but I want it to be a number value. Something we have to do here when we get that error in these calculations. So as you can see, it's at 0, but I'm going to show more values. So I'm using the increase the decimal, the number of values after the decimal. And so as you can see, it's at 0.00004. So now that we have our p-value, okay, and that's again between the groups, okay, so our goal was to compare the average daily sales across 3 different locations And we wanted to know if there is if they are all equal or if there's a difference, right? We always want to measure the opposite of what we believe. We believe that at least one location average sales is different between the groups. Okay. And so if we look at between the groups, we see our alpha here. It's at 0.004. Then we come up here in our decision and we will put on our decision the p-value at 0.0004. Since 0.004 is less than 0.05, we reject the null hypothesis. So we can come in here and reject the null hypothesis. Go ahead and do my strike through. I know strike two. So I strike that out. I'm left with my alternative hypothesis. So my alternative hypothesis is that at least one location average sales is different. Okay, so now I know that one of these locations is different and all the same. So what would be my business decision in this case? So it could read something like this. At the 0.05 significance level, okay, there is sufficient evidence to conclude that daily sales differ significantly among Oakdale, Ceres, and Salida farm stands. Okay, so that would be what I would conclude based on running the ANOVA, the one-way ANOVA test using a sample from each location. Okay, the help is here as well. It tells you use data analysis, ANOVA, single factor, select the entire date range, which we did, the data range, sorry, including the headers, and then compare the p-value to alpha. Compare the p-value to alpha, and we just did that. And if it's lower, our decision was that we would reject the null hypothesis, which we did, which left us with the answer, which is at least one location's average sales is different, which proves what we believed, okay, in this case. So that's the one-way ANOVA. Let's go ahead and move on to the two-way ANOVA. And in this case, I'll walk us through, and this one is without replication, which we will go through. So let's go ahead and let me run this here really quick. So did I add these on here yet or no? No, I did not. All right, so let's look at this problem here. So this problem here is test 3 fertilizer brands on almond crop yields, use 4 different soil plots as blocking variables to isolate soil effects. Again, I really recommend to get a better handle on these to kind of go back here and look at why we're using this. So example, we want to test 3 different marketing displays for selling sports trading cards. We use different retail store locations as our blocks. By blocking the data by location, we strip out the variations caused by neighborhood foot traffic so we can clearly see the true effect of the marketing displays. Okay, so we want to make sure that we fully understand whether fertilizer brands on almond crop yields, if we use 4 different soil plots as blocking variables to isolate soil effects. So what would be our null hypothesis? Our null hypothesis for this one would be assumptions, right? So in this case, put that in there, we believe, wrap it a little bit bigger. So our null hypothesis is that they are all equal. There is no difference between the fertilizer brands, okay? And our alternative is similar to the previous one, at least one, okay? At least one brand has a different yield, or there is a difference, whichever one. 0.05 would be our alpha. Our test statistic we're going to be using, and this is the one that we discussed. This is going to be without replication. Okay, so we'll show that here in just a second. And our decision maker is going to be whether or not the null hypothesis will be rejected if the p-value is less than 0.05. Okay, so let's go ahead and run our tests. So our test, I ran it here, but I'm going to go ahead and run it again. So I'm going to go to data, data analysis, and in this case, I am going to choose without replication, which is here, and press OK. And as you can see, I ran it earlier. Oops, rid of that. I ran that earlier, and that will, what we do here is we highlighted all the areas here. I used labels. I put my alpha at 0.05, and I wanted my output to be right here, F21. Once I ran that, okay, just let me see what I'm doing wrong here. It's not liking it for some reason. But if you ran that, try to run it here without application. All right, and then 0.05, we want the, it's fine, there it goes. All right, so now, here's my data. Again, you could see all the plot information here. Again, these are your sums, your averages, and your variances, and these are by the brands. And if you recall, we had the plots here, and then we have the brands here. And so that's the data that we are given. So now we're going to go back, and now we're going to see the data for this. We're going to get p-values, okay, that we are going to use here. And in this case, the columns and the rows, both of them, we remember we get an error here. What we could do is we could go here, change it to a number, and then we can add more values. So as you could see, both of these values, both of these p-values for both the rows and for the columns, okay, for the rows, for the plots, and for the brands, okay, these are both less than 0.05, okay? So what does that mean? So what that means is that we go back here. So what that means is that the columns, both of them being at 0, we reject the null hypothesis. Okay, so let me see here. Let's put some values in here. So what were these? There were, change the values on these. So 0.05 is the rows. So they're both kind of the same. Okay, so wrap these. So at 0.0000, I'm just going to put maybe not the right amount of zeros, but so they're both here or something close to these values. So in this case, we're going to reject the null hypothesis. So in this case, I have my information, so I'm going to go ahead and do my strike through and that to be in red. This always helps me because now I have my answer. If my null hypothesis is not correct, then my alternative hypothesis is correct. At least one brand has a different yield. Okay. So how would we state this? So if we go back and need to rewrite this, we're going to state something like this. There is a statistically significant difference in almond crop yields depending on the fertilizer brand used. Additionally, the different soil plots also had a statistically significant impact on the crops. So again, this basically tells us that both the rows and the columns, which were the rows is the plots and the columns, they are different. Okay, depending on the plot, depending on the brand, there is a difference between those. So our next step is to further dive into this and figure out what does that mean? Which one of the brands, which one of the plots, what which ones together had a difference and why. That's the next level of testing that we do. Okay, this one just proved that there's a difference. Then our next step is to find out which ones and why. Okay. So again, in the Excel help, it states it right here. Use data analysis, ANOVA two-factor without replication. Check the p-values for both columns, the fertilizer and the rows, the plots. Okay. So if you wanted to, the rows, these are the plots. These are the fertilizers. So if you wanted to, just add that there so you know which one you were doing. Okay. But both of them are below or less than the 0.05. Now, if one was higher than the other one was lower, so for example, if columns, if the fertilizer came in as higher than 0.05, we would conclude that the plots had an impact, but not the fertilizer. So again, just an example, but in this case, there is a significant difference in both the plots and in the brand of fertilizer. All right, so let's go on to the next one. And in this one here, we're going to use the two-way with interaction. So if I wanted to read, well, what is that exactly? Well, we can evaluate customer wait times at in and out based on ordering method. Okay, drive-through versus inside the register and time of day. ANOVA will give us a p-value for ordering method, a p-value for the time of the day, and a p-value for interaction to see if there's an effect of the time of day changes depending on whether the customer uses the drive-through or walks inside. So it's going to tell us if there's a difference. So let's run this here. So our null hypothesis in this case, let's look at our scenario. So our scenario states that evaluate the customer satisfaction from 1 to 100 based on store location, downtown versus the campus location, and time of the day, morning versus afternoon. So what would be our null hypothesis? We always are going to test the opposite first. So our test is going to be that there is no interaction effect between store location and time of day. And this one is going to read, our null hypothesis, or alternative hypothesis is going to read, there is an interaction effect between location and the time of the day. Okay. So our alpha is going to be, again, 0.05. Our test statistic, we're going to use the two-way with replication. Okay. And we are going to again, reject the null hypothesis because we're using p-value. We're going to reject the null hypothesis, in this case, if the p-value is less than 0.05. So let's go ahead and run our tests. And again, we're going to use, in this case, ANOVA two-factor with replication. So I'm going to go to Data, Data Analysis, and then choose a two-way factor with replication here, with replication. So I'm going to then, in my dialog box, I'm going to enter the values. I'm going to highlight all of it, the location, the morning, afternoon headings, and the location, downtown versus campus. And this is important because it says rows per sample. So we only have 2 samples, but each sample, right, we have morning and afternoon. And so each sample has 3. Each location, sorry, has 3 samples. So I have to make sure that that's stated correctly. And that says it here in the help as well. It says use data analysis two-factor with replication. Rows per sample is 3. So rows per sample is 3. Look at the interaction, the p-value, to see if the location and time interact. Okay, we want to look at the p-value to see if the location and the time interact. So we're going to p-value. I'm going to just drop it here and press OK, and then you should get this. Okay, again, here's what we have. We have just some summary data of the morning, afternoon, okay, morning and afternoon. And then we have downtown campus versus downtown versus the campus location. And then we have the total of both, okay? Gives us the sum, the average, and the variance. So what we care most about here is here's our p-values for the sample and for the sample and the columns. Okay, this is morning and afternoon. And so we care most about is there an interaction? This is what the ANOVA tool tells us here, if there's an interaction. Okay, as it states here, okay, as it states at the end of this, it says, look at the interaction p-value to see if the location and time interact. Again, we're trying to figure out here, evaluate customer satisfaction based on the store location and time of the day. And we want to know if those two have an impact on one another. Is there a difference? Okay, is there a difference? We tested that there is no interaction between those, the store location and the time of day of when somebody visited the store. But what we believe is that there is an interaction effect, meaning when somebody goes into the store and what store they go into, they're going to have a different experience. So they're not going to rate it the same. So once we tested it, we find that our p-value under interaction is 0.0005. So again, what we talked about is the rejecting the null hypothesis. The null hypothesis is going to be rejected here, and I'm going to go in here and I'm going to do my strike through, and I want the color to be red just because it helps. And then I am left with, there is an interaction effect between location and time of the day. And so what I am going to say under the decision for the interaction, p-value is 0.000059. Since the p-value is less than 0.05, we reject the null hypothesis. So what is my outcome? So my outcome is, here is based on the p-value being less than the alpha, we find that there is a significant interaction between location and time of day, meaning satisfaction levels throughout the day behave differently depending on which store the customer visits and when. Okay. So those are the three. Again, hypothesis testing, we did t-test again last week. We're using ANOVA this week on different variables, showing you how they are used. I hope this example was helpful. Again, you have the steps outlined in your, let's see here, we have those steps outlined in the student guide. So you have the student guide as well under the module 12 where the Excel spreadsheet is. And this kind of walks you through step by step on how to complete these problems as well. Okay. This, along with the Excel spreadsheet itself, gives you all the data that you need and the steps that you need to actually complete the analysis. Okay. And I hope that going over these, and especially I know the writing the null and alternative hypothesis and the outcome itself, I think seeing this, it should make a lot more sense to you. Okay. Enjoy the video. Please let me know if you have any questions, and we will talk soon. Thank you.